Good day. The title of this research is Automated Warehouse Optimization Using a Genetic Algorithm and Multi-Agent Pathfinding. My name is Simon Rosen, and my supervisors are Stephen James and Christopher Cleghorn. Automated warehouses are a large and growing industry, but their layouts are still designed by human experts. This is an expensive, time-consuming, and likely to be suboptimal. Instead of a human, a genetic algorithm can be used, as is the case with our research. What is an automated warehouse? This is a warehouse operated by robots, where these robots pick up and deliver packages from storage locations to drop-off locations. The number of packages picked up and delivered determines the productivity of the warehouse. Another important aspect is the percentage of floor space usable, as this will affect costs. Here is an example of an automated warehouse, where on the left you can see the drop-off locations, and the majority of the space is taken up by the storage locations. And you can also see a few robots populating this space. The current approach for designing automated warehouses and warehouses in general is for human experts to design them. This is, however, expensive and time-consuming. Our solution is to use a genetic algorithm. We optimize an automated warehouse using a genetic algorithm with multi-agent pathfinding in the fitness function and NSGA2 as the selection operator. On the right, we can see the fitness function, where a warehouse layout is inputted and then the percentage of locations reachable is calculated, and the number of unique tasks completed is also calculated using multi-agent pathfinding, with the specific algorithm being token parsing. And the percentage of locations reachable is an indicator of usable floor space, and number of unique tasks completed is the number of packages picked up and delivered from unique pickup locations in a set number of time steps. And as you can see, there are two objectives that form part of the fitness, and thus this is a multi-objective optimization problem, which necessitates NSGA2, which is a selection operator that is very good for conflicting objectives and has been used with great success in many multi-objective optimization problems. So you can see this is the general structure of the GA. And the warehouse representation is as follows. It's represented as a 2D grid where the portions being optimized are the storage locations, as you can see over here, and the drop-off locations and robot resting locations stay static, where the robot resting locations are locations where the robots can rest forever without colliding with other robots. The baselines we use are the random baseline and a human expert baseline, where the random baseline is the storage locations are completely randomized, and the human expert baseline, the storage locations were designed by a human expert, and this comes from a multi-agent pathfinding baseline that is very widely used. And to measure our results, we use a multi-objective optimization algorithm, a metric called hypervolume indicator, or S metric, and this indicates the quality of the Pareto front, where the Pareto front is the set of best trade-off solutions. And in the 2D case, the hypervolume indicator is calculated by calculating the area between this Pareto front and a given reference point. Lower is better here. We can see that the expert performs the best, which is to be expected since its percentage of locations reachable is optimal at 100%. Next is the genetic algorithm, which performs better than random, which does the worst. In terms of here we look at the objectives separately. On the left, you have reachability, where you see that, as expected, the real warehouse does the best, followed by the genetic algorithm, and worst is random. And then next, with productivity, you can see that the genetic algorithm performs the best, followed by the real warehouse, benchmark, i.e. the expert benchmark, and then followed by random. And here's an example layout. And in conclusion, our genetic algorithm creates layouts better than the random baseline, and the layouts are better in productivity metric than expert made baseline, but worse in floor space usable. And then finally, here is the multi-agent pathfinding algorithm being evaluated on an example layout. The colored dots indicate the agents, and their task is to go to one of the storage locations, i.e. the black squares on the right, pick up a package and drop it off at one of the drop-off locations. So you can see over here there is 60 agents, and that is why some of them aren't yet engaged with tasks.